Morning, everyone from Berkeley, California. Welcome to the Data Colada Seminar Series. And today we're going to have a couple of great speakers, Dan Goldstein and Jake Hofman, who are joining us from Microsoft Research. In addition, we have 4 panelists who are joining us. And those are Brad DeLonga, Miriam Jenny, Shane Frederick, and Rick Larrick. In addition, we will have Yuri Simonson and Joe Simmons with us today. So I will give the floor to all of them once all of our technology gets settled and we can listen to their presentation.
My name is Dan Goldstein. I am broadcasting from the Upper East Side of New York City, and I am co-presenting today with Jake Hofman. Hi, Jake. Who is in the wilds of the Hudson Valley in a cabin retreating from the pandemic. There is a poll that you will see on the screen at the top, pollev.com/DanGoldstein941. You can go there right now. You can load that up in advance, and at some point during this talk, there will be a poll that you can participate in, and we can send you the results after the talk today. That being said, let's go. We begin in the land of ice and snow on a snowy mountain lake at sunrise. The camera flies over a snowy field to the edge of a woods where it moves up in the air. It must be a drone shot. And over a cabin with footsteps extending out from the cabin, away from it. We follow the footsteps up to a snowy mountaintop, and right behind the shoulder of you, the protagonist, who is hiking onward down to a pristine mountain lake. Here's the pristine lake where you practice your sport of boulder sliding. That's right, boulder sliding, sliding a boulder on ice as far as you possibly can for money and for the feeling of victory. It's a bright, clear morning. It's eerily quiet, but you are distracted. All you can think about is Blorg. Who is Blorg? Blorg is your enemy. He's your competitor. You went to the same kindergarten as Blorg. You went to the same ice high school as Blorg. You've competed for years against Blorg, and the most frustrating thing is that Blorg is equally good as you, and you are heading into a major competition against Blorg. In this competition, you will have one chance to slide your boulder on the ice, and the winner will get 250 ice dollars. And the symbol for ice dollars is NID. The N is for new. You see someone walking towards you on the ice. You can tell immediately from their goofy walk that it's your coach. We won't give your coach a name or a gender. Nobody has a gender in this story. You can just impose on this story what you want, but your coach comes towards you and gives you some information. This is what your coach tells you. There's a special boulder that you can rent in the competition, and it slides further than the standard boulder. And Blorg will not rent this special boulder, but it's perfectly within the rules for you to rent the special boulder. It's kind of like investing in these actual Nike shoes that cost $250 and are supposedly able of making you run 4% faster. So your coach is naturally quite interested in the prospect of you using these and figuring out how much you might pay to use the special boulder. And your coach shows you some data. So this is the results of an experiment. In the land of ice and snow, they have very good artificial intelligence. They built a robot that throws exactly like you, which means exactly like Blorg. And this robot slid a boulder 1,000 times, slid a standard boulder 1,000 times in a control condition, and 1,000 times in a treatment condition. And this was the results of the experiment. Here we see the average sliding distance, the mean in each condition, and error bars representing 2 standard errors around the mean. Many of you psychologists are used to 1 standard error. This is 2, so think about that. And then the question is, what is your chance of winning the competition against Blorg? what's the probability? So what we want you to do is go to that poll link now. I'm going to activate the poll. Don't blunder and say something less than 50% because you and Blorg are equally skilled. You will slide 50% if you both use the standard boulder, but you're using this special boulder which slides even further. And you think about what your coach told you, that boulder sliding is a game of centimeters. This has a 4-meter difference in the amount of distance that it will slide. So give you a moment to enter your answers. Thank you, Jake, for the music. Looking at the panel, one thing about the Data Colada seminar is that you are able to pick your own panelists. I'm very, very happy. Some of my favorite people are here on the panel. So we were asking you about your chance of winning, and we showed you a plot, very much like a plot that you would see in a psychology journal. If you're like most people, when you saw this plot, you answered something between 80 and 90%. Your chance of beating Blorg using the special boulder would be between 80 and 90%. This is what most people in our studies have answered. But you could have seen this plot instead, right? And so here we have the results of an experiment. Again, it was the sliding robot. Here the bars show 2 standard deviations around the mean in the sliding distance of the boulder. And again, the question is, what's the probability you would win if you use the special boulder and Blorg used the standard boulder? Here, most people say something between 60 and 70%. So they give a lower number when they see this plot. What our talk today is about is the idea that these are 2 different and easily and often confused visualizations of the same underlying data. And the correct answer in both cases is 57%. So if you use the special boulder and Blorg uses the standard boulder, there's a 57% chance that you would slide your boulder farther than Blorg. And this is what's called the probability of superiority. It's also called the common language effect size. And what we're going to talk about today is this number 57. So we really want you to remember this, 57%. I don't know how you're going to remember it. Maybe you could think it's 3 times 19. Maybe you could remember Heinz 57 ketchup, but it's going to come up a lot, trust me. And at this point, I'm going to turn the audio over to Jake, and he's going to talk about this effect and why we think it happens and how we measure it.
Great, thank you, Dan. So this idea, why does this happen? Why is it the case that when we show people the standard error bars, they give an answer of something like 80 to 90%, and when we show them the standard deviation bars, they give something like 60 to 70%, right? And the idea here is simple. Error bars are confusing. Even for us highly trained scientists, so you might not know the difference, or you might not notice the difference, but either way, you can get confused pretty easily. And what I have here are 2 articles, one from Nature Methods magazine from 2013 on the left, which is all about how people confuse error bars, how they sometimes don't say what type of error bar is even in their paper, how they asked a bunch of scientists and they were confused about what they were seeing, and so on. And the other on the right is a retraction notice from a meta-analysis paper looking at blood pressure, where in the meta-analysis, they pulled data from an existing paper and thought they were pulling standard deviations, but pulled standard errors, right? And they ended up having to retract this analysis. And, it doesn't help that, the words are almost the same. Standard deviation, standard error. The visual markers are the same as you're seeing here, these lines with the ticks at the end, but they have super different meanings, right? And the way we like to sort of sum this up in one little haiku is people confuse a well-estimated mean with a certain outcome. And so if you look at the plot on the left, showing this 2 standard errors above and below the mean, what that's telling you is that you've estimated the mean in each group very precisely. So it's showing you inferential uncertainty about this statistic that you're estimating. Whereas on the right, when you look at standard deviation, that's showing you the variability in individual outcomes. It's no longer about your estimate. It's about how much individual outcomes vary around the mean. And these are 2 very different senses of, in one case, uncertainty and the other case variability, but there's very little between the wording and the visual to tip you off to that when you look at these two. And so to make that a little clearer, and I think probably many people on this call right now know the difference very well, but it doesn't hurt to go through an example, and a very fun example at that one, because it's one that Cohen used in his textbook when he introduced effect sizes. So Dan, if we can go to the next slide, what you'll see there is a picture of the heights of 15-year-olds and 16-year-olds. So Cohen actually makes this analogy in his textbook. He says, imagine that you have the full population pictured on the left of 15-year-olds who have an average height of 170 centimeters and 16-year-olds who have an average height of 174 centimeters. So they differ by 4 centimeters. The standard deviation in both groups is 15 centimeters. So if we compare that difference, the mean difference of 4 centimeters, to the standard deviation of 15 centimeters, that's about a quarter of a standard deviation, about 0.27 standard deviations difference between the means, and that's Cohen's D measure. It's how many standard deviations apart are the means in each group. And so he introduced this in his textbook, and he actually made this analogy, and he said this is like the difference in heights between 15-year-olds and 16-year-olds. And as Dan mentioned, that 57% number is going to come up a bunch in the talk. It turns out this is exactly the number in Cohen's textbook. If you were to randomly sample one person from each of these groups, there's a 57% chance that the randomly selected 16-year-old would be taller than the randomly selected 15-year-old. So that's what we mean by the probability of superiority. So Cohen's D and probability of superiority are two different measures of effect size that have to do with the underlying distribution. Where we know the full population, we would be able to compute those things. Of course, we never get to know that full population. So let's imagine what would happen if we instead sampled some data from. Let's say we took a sample of 25 people and we computed the means and 2 standard errors above and below the means in each group. We might get something like this. This is an actual real sample. I ran a simulation just to make sure I didn't mess anything up. And what we would do is maybe visually look at the overlap between the error bars. Keep in mind, these are 95% confidence intervals, so 2 standard errors above and below. And we might do something like a t-test, and we'd get a p-value of 0.59, which would tell us that, you know, we can't easily sort of reject the null that these came from the same distribution. So being good scientists, we might know that we need a bigger sample size. Maybe we up this to 100 people, and we take our sample. And we might get something like this, in which case, you know, now we get a p-value of about 0.03. And so we can say, well, it's reasonably unlikely to see this data under the null. But, you know, maybe we're super great scientists and we up our sample size even more. We go for a sample of 400, right? And now we get a super tiny p-value, super duper unlikely that we would see these data under the null where the means are the same. And very tiny confidence intervals on both of these estimates, right? And so as we add more and more data, we see our error bars shrinking. And the thing I want to point out about this is nothing has changed about the true population on the left. It's simply that as we get more data, we can drive that p-value down, we can drive the standard errors down, but the underlying effect size, the real difference between 15-year-olds and 16-year-olds hasn't changed at all. And one way to kind of emphasize this is the overlay that Dan has just shown, where I've actually shown you now the individual points coming from each of the draws in sort of faded behind the estimates. And so, you know, seeing this, you might get a very different sense from the type of thing you might see in a published paper. So imagine, instead of me showing you this sequence, I was just a good scientist. I went and got 400 samples, and I computed the means and confidence intervals, and I showed you this plot, right? And this is just the default of how my R package plots this visualization. You'll notice one thing it's done is that it's zoomed in to the range of the error bars here, right? So we're sort of magnifying. And when you look at this, you get a pretty stark sense that there's a clear difference. The thing is that clear difference is in the means. It's in our estimate of the means, right? And if we go back and show that last plot that was on the previous page, you can see that same difference when you see the variation in the data looks perceptually quite different. And that's kind of what we're focusing on here in this work, which is that even though in theory, the same information is contained in the top plot and the bottom plot, it's very hard when you see the top plot to sort of say, okay, those are standard errors. Let me blow them up by a factor of 20 and I'll get a sense of the individual variation in the data, right? When you see something like the bottom plot, that really pops out at you more directly. So that's the idea behind this work, right? The call for reporting effect sizes is not new. It's been going on for a long time, since Cohen wrote his book. There are some shifts. It's getting a little better. People are reporting these things. But the visualizations that we see primarily are of the standard error type. They emphasize statistical significance by showing standard errors, right? And so the question we looked at here was, how much really do these different visualizations of statistical results affect perceived effect sizes?
Jake?
That's a mouthful. Yes.
Could you say a little bit of why we should care about the probability of superiority as opposed to other metrics? One thing I've been thinking, if that was the ultimate goal, we probably would compute the probability of superiority.
Yes, that's great. I think it really depends on the scenario. So one big thing I want to throw in here is it's not always the case that you should care about probability of superiority, or always the case you should care about any metric. I think when you think about the scenario Dan is talking about, let's say, you're really going to run a race and you want to figure out how much you should pay for these shoes that are going to boost your performance, right? This is a very individual level decision, and you might have a 0-1 payoff, right? You win or you don't. But a policymaker might have a very different setting where they really care about a mean difference if you're going to implement a policy that affects 100 million people. And so maybe you don't care, and maybe you have a payoff that's linear in that mean difference, for which case probability of superiority would not really be the right thing to focus on. So we're looking at a very specific scenario. We think this scenario is relatively common in sort of individual level decision making, but maybe not, for instance, at the policy level.
Can I just ask a question regarding that as well? Because when I was thinking about it, I was thinking it's not even always inferable from the data, because imagine you had two groups of people, like group X is given treatment A and group Y is given treatment B. X and Y are just randomly assigned. But what you could compute from the data is the probability that X given A is greater than Y given B. But that's not really what you want. You really want to know what's probably that I would do better if given treatment B than given A, and that may be 100%. Right? So if you look at the data, people are randomly assigned to two conditions. Right? You would infer from the data that the probability of superiority is 51%, but the real probability is 100%, because treatment B is just better than treatment A, and there's a whole bunch of other things that also affect longevity. For example, genes, gene-person interactions, and lots of other things. But I don't think you actually can, in many cases, even can compute it from the data. You couldn't know it. And I think would be a pretty good example. If the drug is just better, it helps everybody, but lots of other things matter too. And so when you end up looking at the data, you'd say the probability of superiority is 51%, but actually it's 100, or something in between. You don't really know for sure. And so I think it's kind of a weird. I mean, I'm kind of following on what Yuri said. To me, it's weird in a couple of senses. First of all, there's other things you could compute, and second of all, you often can't compute it from the data.
Interesting. I think it may fall in, a category of questions about, effect size more generally. It may have to do, Shane, if I'm understanding, maybe it has to do also with sort of the quality of the randomization, for instance.
No, I'm assuming perfect randomization. Everybody's like, we got like a huge bunch of people are randomly assigned to two conditions, and you give one group A and you give another group B. There's variability, of course, because things matter other than what they're given. Right? People live long or short for all sorts of reasons, including the drug that they're given. And if you look at the data, you'd say there's a 51% chance of superiority. But I don't really care about the probability of someone else given a different drug versus me. I care about the probability of me given one drug versus the other drug. And that might be 100%, right? We don't know. We can't.
No, you don't know. But if you're trying to facilitate a decision to buy these shoes or not, you also don't know what the interaction between you and the shoes is going to be, right? They could hurt you. They could help you, but you're just trying to make some decision here and figure out what to expect. It also correlates, all these things like hang together, right? So Cohen's D, probability of superiority, number needed to treat, number of standard deviations you can expect to move on average. They all do hang together. So while you could find faults with individual ones of them. They certainly vary proportionally with the effects that we expect to see with our bare eyes in the real world when we implement these treatments. But I agree, yeah, if you're omniscient and you kind of know how each person's going to sort out, then you don't really need to like read these popular press articles and figure out if green tea is going to like make you live longer or whatever.
Hey Dan, this is Rick. You just mentioned number needed to treat, and I find that a kind of intriguing statistic. Do you want to give a thumbnail sketch of it? Because I think it also might be a more useful tool for explaining the benefit of an intervention.
So in the interest of time, I'll just refer people to Christopher Magnuson's Cohen's D calculator, which is this amazing online website that lets you move two normal distributions apart and shows you how probability of superiority, number needed to treat, and so on vary, and also offers good explanations of what those things mean. But in certain contexts, given certain assumptions, it's the idea that you'd expect to see like a marginal person in the treatment group have a different outcome than somebody in the control group. So if it's like being cured from a disease, you might need to treat like 100 people before you expect to see one who's actually cured from the treatment. All right, Jake, I'll hand it back to you.
Okay, great. So what I'm going to do is just more carefully walk us through, in a sense, you just did in the poll, a version of the experiment that we had thousands of mechanical Turkers do. But what I'm going to do is just walk this through a little more slowly so you have all the details. But if you remember the punchline from what Dan presented, I'm just going to give you the more detailed version of that. So we did an online study on mechanical Turk. We randomly showed people this. We showed people this narrative and randomly assigned them to see either the standard error or the standard deviation condition. And then we measured two things: how much they were willing to pay for that special boulder, that special piece of equipment, the analog of the Nike shoes, and what they thought their probability of winning was if they used it. And that's the poll question that everyone on the call answered earlier. We are big fans of aspredicted.org, so we have pre-registered everything there. And as I said, these all involve thousands of people. Let me walk you through the different screens that these folks saw on the experiment. The first screen told them that they're in this sliding competition. They will get 250 fictitious ice dollars, and that there is a special boulder that they and only they can rent that tends to slide farther than the one that their arch nemesis Blorg is going to use. And so we tell them we want to know how much you're going to pay for this thing you'd be willing to pay. But first, we're going to give you some background information. So here's the first bit of information we give on the next screen. Which is about the average sliding distance of the standard boulder. We give everything in frequency framing. So we say the past 1,000 times when you've slid this boulder, it's gone 100 meters. We tell you about the variation in your sliding distance. So we tell you that 95% of your throws go between 70 and 130 meters, evenly distributed on both sides. And then we give you some uncertainty in estimating your true average. We say, we think your average based on this data is 100 with a 95% confidence interval of 99 to 101, and we explain what this confidence interval means. And then we re-emphasize the point that you and Blorg are identical when you're using the standard equipment. They click through to confirm, go to the next screen, and this is where they see the visualization. So we tell them about the special boulder. We say, here is a picture that describes exactly what the special boulder has been observed to do. The average distance is between 103 and 105 with a mean of 104, right? And that's our 95% confidence interval. And again, we repeat that explanation and point them to the graph to take a look. Then they get a slider down at the bottom that says, what's the most you'd be willing to pay? That slider's initialized over to the right. They have to move it. Even if they move it and move it back, they have to move it in order to continue. And we parrot back a sentence that says, this indicates you're willing to pay so much for the boulder. They click through. Then we ask them the analog of the question you all answered earlier. We do it in a frequency framing instead of a probability framing. So if you were to compete 100 times where you had the standard boulder and Blorg had the standard boulder, what's your best estimate of the number of times you would win? This was essentially an attention check. We want people answering 50 here because we gave them many reminders that they're equally matched with Blorg. And then down below, we say, if you had the special boulder and Blorg had the standard boulder, what's your estimate of the number of times you would win? And again, they answer there and submit. And that's the end of the experiment, very simple. The other condition they could have seen was the standard deviation, in which case the graphic changes and the description, instead of saying this is the uncertainty in your average distance, it says this is the variation in your distance. So those are the conditions. Dan, drum roll, here are the results. So we have lots of meta thinking to do because I'm going to show you plots with standard errors about people seeing standard errors. So let me walk through this very carefully. The punchline, if all the language is confusing, is that people are willing to pay quite a bit more for the treatment when they see the standard error visualization. So on the right, what you're seeing is that people paid an average of 80 some odd dollars when they saw the standard error visualization. And on the left, when they saw the standard deviation visualization, they paid $56, $57, something like that. Now, this plot is showing 95% one standard error above and below the mean. From that, you can see the p-value is very small. It's very unlikely that these willingness to pay distributions are the same. It's very unlikely we'd see this data if these distributions were the same. It would be a little dishonest in a talk about showing outcome variability for me to quote this as the plot that you see. Instead, Dan, if you click through, what we have here are the standard deviations in willingness to pay, right? And so kind of the point of our paper is that if we show you this version of our results, you'll probably think they're less impressive than if I show you the previous version. And yet most of us print papers with the previous version, right? This corresponds, by the way, to a Cohen's d of about 0.42. We are well aware that Cohen's d is very hard to estimate and that our friends at Data Colada have many issues with estimating effect sizes in the lab. We're going to brush those under the rug for the second. We can talk about them after maybe. But we think that even just seeing this version of our results, sort of camera A, camera B, standard errors, standard deviations, makes a big difference in how you receive this information. We see the same type of thing on the next slide with probability of superiority. So again, as Dan quoted, if you're like most people, and we should say we did this on Mechanical Turk, but we've also run this poll with members of our own lab who we hold in high regard, and many of them have responded with something upwards of 80, sometimes 90, sometimes 99, with a certain number of significant digits based on an inverse cumulative normal distribution, because they're very clever and they start calculating things. Whereas people who see the standard deviations plot say something closer to this mid-60s range. And again, when we plot this with standard deviations as the error bars instead of standard errors, we get a Cohen's d. You can see the difference here. It's reasonably large in terms of an effect size. It's a Cohen's d of about 0.74. So people are really overestimating these things in both cases, but much more so in the standard error case. Dan, if we can go to the next slide. We did a bunch of other things. Because of time constraints, I'm going to zoom through these other things. The first thing we did was to say, well, maybe if you show people these standard error plots, but in the text you mention the standard deviation and you've got all this information in the caption, maybe that mitigates the effects. It turns out that doesn't work, unfortunately. It doesn't really move people very much. We also tested sensitivity. When we showed them the boulder, we had one that was sort of a small effect size that moved you 4 meters. We had another that was a large effect size that moved you 16 meters on average. We see people are sensitive there, much more so in the standard deviation condition than in the standard error condition, but they are able to detect that difference. And then we looked at other visualizations. So the two we've been talking about are the two on the left here, the standard errors and standard deviations. We did sort of a weird hybrid where we took the standard error plot, but we rescaled it to include the range of the standard deviation plot. So that's that third plot there where you can kind of see there's that difference. You can see the standard errors, but it's explained to you that the axis has been rescaled to show the variation of the data. And here we see that this helps people, but it doesn't get them quite as far as the standard deviation plot. Maybe the more interesting one, and this is a really great innovation from our co-author, Jessica Holman, which she calls HOPS, or hypothetical outcome plots, is to use the power of animation. It's an animated GIF, which is hopefully coming through on Zoom, where you're seeing random samples drawn from each arm, and you can directly compute something like a probability of superiority by just looking at how often the bar on the right is higher than the bar on the left. So we think these things are pretty neat. Dan, if you click through, we'll get little markers on each one. So the rescaling helped somewhat, but not enough. In our opinion, the hops really performed very similarly to the standard deviations, which was pretty nice. The other thing we did, which I'll show on the next slide, is that we elicited full probability distribution. So we wanted to know what was in people's heads. Thankfully, Dan, along with Eric Johnson and Bill Sharp, had developed a tool called the distribution builder, which allows a sort of lay person to go ahead and redistribute the mass of a probability distribution until it represents what's in their mind. And so, Dan, if you click through, we'll see that was the original that Dan built. Here is a wonderful version, which I want to plug. Quentin Andre has done a great job of porting this to JavaScript. It's a simple thing anyone can throw in their own experiment. What you're set up with here, after you answer all those other questions I showed, it says if you and Blorg were to complete 100 times where you had a standard issue boulder, how many slides do you think would land at each distance? And you have 100 throws, and you can click plus or minus in the little boxes to make the amounts go up and down until you've distributed all 100 throws. So you do that for the standard boulder, you do that for the special boulder, and we collect all those data points from all the participants. And here's an aggregation over something like 400,000 placements of people's balls into these bins. The lines that you're seeing are the true distribution, and the bars are from people's estimates. So if you look at the plot on the left, that's where the visualization showed standard errors. And what you're seeing is that the bars are really much tighter than the lines. People are viewing in their mind when they see those bars, they're thinking that the distribution is really pretty limited to where the bars are. Whereas if you look on the right, when people see standard deviations, right, that aggregate distribution, the wisdom of the crowds there is kind of working pretty well. People have a reasonable representation of what's going on in the underlying distribution. So Dan, one more slide here, which is just on a few other things we've done and are doing around this before I hand it back to Dan. We're really interested and excited about this idea on communicating sort of visually and in text better versions of scientific work. With Yesol Kim, who was an intern with us last summer, we've looked at text-based communication. And actually, that's where this wonderful idea of the height analogies came from. So Yesol went back and found this analogy in Cohen's textbook. We took it and we did a within subjects experiment where we first showed people sort of the standard deviation information, got their estimates, and then we said, here's one more piece of information. And, based on this, do you want to update your estimate or leave it alone or whatever? And so if you directly tell people probability of superiority, so over here in this very top magenta sort of bar, when we show people this extra bit of information, we're saying, if you were to play 100 times, you would win 57. That's the probability. We're giving them the probability of superiority, and we're asking what they're willing to pay. It cuts their error in willingness to pay relative to the normative value in about half. And if we show people the height analogy, saying this is, the special boulder would beat the standard boulder about as often as a randomly selected 16-year-old is taller than a randomly selected 15-year-old among American women, we get a very similar error reduction. We tried a bunch of other things, including telling people variance directly, giving them a weather analogy, like how often February 15th would be warmer than January 15th in a given city. And we looked at categorical statements about whether there was a small, medium, or large difference. And so, we're pretty pleased about the idea that you could imagine communicating these types of analogies in something like a newspaper article to give people a more clear qualitative understanding and quantitative understanding of the effectiveness of a treatment. So that's one bit of work, which we will have a link to the paper later. Yuri, is that?
Yeah, I had another question. Have you run experiments varying the effect size and the variance? Because I was picturing a smaller effect, let's say an effect that's powered for 70% or 80%. It could be that people with standard deviations underestimate it, and with standard errors, they get it right.
Yeah, so we did do this small and large effect size in the boulder sliding, but we do have some more thoughts, and I'd be happy to discuss that maybe at the end or maybe offline about whether it's a big mean difference, big standard deviations, you know, exactly how you piece apart that effect size and how people perceive it, because I think that's a very interesting question. Yeah.
I had something similar to, again, kind of following from Yuri's question. I was just thinking, like, if you ask people, we had 10 men on one side of the scale, 10 women on the other side of the scale, what's the probability that it tips down on the men's side? I would guess that people would probably underestimate the true probability of that, which I would assume is very near 100%. Even though if there's one man and one woman, it would be maybe 65%. And so I'm just trying to figure out, like, would people, are they, like, what would be the, like, what level of aggregation would constitute the error that people are making?
Yeah, that's a great idea. I think it'd be fun.
Yeah, but I think I saw a talk by Joe Simmons once, and he said that the sample size you need to reliably detect the difference in weight between men and women is surprisingly large. I think you said it was about 80 per condition, Joe, is that correct?
It's about 50 per condition.
50 per condition.
In a representative sample.
Yeah.
It depends on the sample, but if it's representative.
And with height, it's just 6, which is crazy, right?
Yeah.
That's right. That's right.
Yeah, that's great. That would be fun to do the aggregation version for sure. So we'll add that as number 3. Number 2 on the list is, you know, we get the feedback that, of course, we did this with mechanical Turkers. They may not be trained in statistics as well as other folks who are actually making decisions based on this. So we're partnering with some wonderful collaborators who I think are on this call, Patrick Heck, Michelle Meyer, and Chris Trebrie, to pilot this on medical decision-making with doctors, for instance, looking at blood pressure medication. So with that, I think I'm going to hand it back to Dan, who's going to give us some very deep, mind-blowing thoughts to close out the talk.
All right, deep thoughts. Number 1, this has all been very meta. In this talk, we are showing graphs to you, graph experts, and the graphs are graphing the results of showing graphs to other people, and we can't even show you the graphs without imparting the biasing effect that the graphs are documenting. So that's just kind of 2, at around 0.75, the effect of not emphasizing effect size is itself a very large effect. And of course, there's an incentives issue here in science. We always want to make our results seem very impressive, except when we're trying to, like, downplay the difference between things. But there's a lot is at stake in the sense that, like, that is a really big effect size if we chose the other visualization, which leads to the next point, which is that it is a tough choice between these 2 ways of showing your results. The one on the left, no matter how well, whether you know the difference between standard errors and standard deviations or not, the one on the left kind of makes me feel like it's a very large effect, and the one on the right makes me feel like it's not such a big deal. Even though normatively I know that they're both the same difference, it's kind of a sad Necker cube in which I can't really hold both in my mind at the same time, and I kind of wish that there was a representation that would let me appreciate both at once without kind of exaggerating one and discounting the other. Luckily, there has been some research that we found in the literature, and by the literature I mean Twitter, in the past few days since we've been talking about this talk, that people are coming up with hybrid representations that try to take all of these things into account. We're friendly with Matt Kay, who is a scientist of the computers, and I recommend you look at the work of the scientists of the computers because they're doing a lot of really groundbreaking stuff when it comes to building new visualizations, and Jake and I are eager to start testing these visualizations on the Blorg problem and similar problems to, like, look at how these visualizations change people's perceptions of these proxy measures. The common language effect size, which is another word for probability of superiority. You remember a few slides ago that Jake showed, it really did have the biggest effect on people getting people to drop their willingness to pay. And so there is a lot of promise, as previous psychological literature has shown, to using probability of superiority as a measure. One last thing I just wanted to leave with this chart, maybe somehow brought on by the Reformation movement that the Data Colada folks had a hand in starting. This is from the appendix of the Nosek et al. 100 whatever author Many Labs project, in which about 100 psych science articles were replicated by Many Labs each. The original horizontal axis in this chart is R, as in the correlation coefficient, which you can convert to Cohen's d. Here I've converted to probability of superiority because I think it's superior. And you can see something really interesting that if you look at the original studies that they were published, if you take like the median one, I know people aren't, it's hard to read CDFs, but here the horizontal red line is showing like the median of the distribution, and then you drop it down to the axis. You can see that back in the day, when you were reading these studies, the median probability of superiority you would have read off that Cohen's d of these published studies was about 70%. So you would think that if you did one of these treatments in your classroom, and you picked one kid here and one kid there, and you gave one the treatment, you have a 70% chance of your demonstration, working, in the sense that the treatment kid would have a higher score than the other kid. When these studies were carefully pre-registered and replicated and measured very, very carefully, we get the curve on the left. And so just to make that a little bit easier to read now, if we look at the dark dots on the left, we see that the median study of these same studies, when they're carefully replicated, has a probability of superiority of about 57%. That's the median of these studies that were chosen to replicate. If you look at the lower left corner there, you can see only 2 of the studies, as they were originally published, were published with an effect size of lower than 57%, right? So it's, there could be some selection bias in which studies they chose to replicate, but it's interesting because you see when you really rigorously replicate these studies, about half of them have a probability of superiority of 57%, which means about half of them have a Cohen's d of about 1/4. And so that's something that I think we should keep in mind for what we should expect from representative psychological studies, given that these ones are representative. Another thing that occurs to me is that back in the day, those studies that we read, they were probably presenting means and standard errors, which we know causes people to inflate these things that covary with effect size, which means back in the day when we were reading these studies, we probably had a mental impression of the effect of these studies that was really big. We probably thought, it's no big deal to move people by 1 standard deviation with a run-of-the-mill psychological treatment. It's probably no big deal to achieve a probability of superiority of 80%. And then when we do these things in the classroom and we find that they don't work about 80% of the time, we start to realize, it's not just pre-registration and file drawer issues and generalizability that like lower effect size. There's this other thing, is that we might have this mental view that effect sizes are bigger than they are anyway, in terms of what effect we would expect to get to the real world. Even if you're in a really good environment for generalization, even if you are looking at studies that have been really well done and there's no file drawer or whatever, we might just have illusions about how big these things are in terms of probability of superiority. So wrapping up, I think it's easy to overestimate the probability of superiority when you're looking at scientific results, especially when you're showing means and standard errors. Displaying outcome variability helps, and Jake and I have been dedicated to putting numbers into perspective for like the past 8 years. It's our big research theme. So we want to leave you with putting one number in perspective. You remember like one factoid from today, it's that this 57% probability of superiority was the median effect in these 100 replications, which is about a Cohen's d of about 1/4. And it's the probability that a 16-year-old is taller than a 15-year-old. So when you're reading an article, if it is like the median of these psych science articles, the effect there is probably something like that somebody in the treatment group would be have a higher score than somebody in the control group about as often as a 16-year-old would be taller than a 15-year-old. I want to give credit to our RAs who helped with the programming and running these experiments when they were at Microsoft. Will Kai, now at Stanford, Management Science and Engineering. Jenny Allen is now in the marketing department at MIT. I also want to credit the photographers who Creative Commons licensed the pictures that I used there in the beginning, and open it up to questions and provide you these links to the papers right here.
Thanks, guys. That was a really great talk. I love this stuff. I've seen it in a briefer form before, and I like it even more in longer form. I just want to kind of follow up on Shane's question that he asked initially, and it seems like for part of your point, you're sort of presuming a mapping between Cohen's D and probability of superiority, but in a between subjects design, like it's possible that, I mean, this is basically rephrasing what Shane said. Like it's possible that in effect, like you have a large effect on 5% of the people, or you have a small effect on 100% of the people. And if you have a small effect on 100% of the people, then your probability of superiority is effectively, if you were able to do it within subjects design, you would actually see that it's 100% probability of superiority. But if it's a large effect on 5% of the people, then if you did it within subjects design, it would be a 5% or 55% or whatever probability of superiority. So, yes, can you just speak to that a little bit?
Yeah, it's a great point. It's something we hadn't really paid a lot of attention to, but I totally see the point that there's this between subjects analogy that sometimes holds very well. Like I think in the boulder sliding thing, there's this normal distribution built into the boulder slide. It doesn't really matter who you are. You're going to have this, kind of shift in the distribution when you use one versus the other, but you can't really guarantee it. Where there are other domains where you could think about your score in the counterfactual world of you having the treatment, and it could be the case that there's a very close mapping between, you can really predict quite well everybody's score without the treatment and with the treatment, and it could actually be quite high. The question is, like, can we sort these domains? Can we categorize which domains are which? And can you yourself predict which of these two worlds you're in when you're trying to make a decision? But I think it's a really good point.
I think another way to think about this, I think it's a great point, and it's definitely something we had not thought carefully about. But another way to think about it, I guess, is you could imagine an ideal world. The reason it has an effect on 5% of people is due to some feature of those people, right? So if we're in a medical setting, imagine we had a magic wand to get all of the features that would tell us precisely why those people are different than the other folks. And so then you would want to know, well, conditioned on those things, right, what is the effect size, right? And so then you're really going directly to the question of just predictive power of a model, right? So I think that would be an argument to say, well, we should look at the predictive power and not just coefficient estimates, right?
You just need identical twin studies.
Right. And really invasive data collection. But yeah, great point. And I'm so glad we came out of this experience with like a whole new thing to think about. It's really something that hadn't occurred to us that much.
In the beginning, you showed the graphs with the error bars and the standard deviations at some point with the data points superimposed. And so I was actually expecting that you were going to test those formats too. And I mean, you did test some view of more data when you tested that one graph on the left when the different data points were just randomly sampled. Well, why not just showing the whole data, the superimposed points?
Yeah. So we got that from Stefan, actually, because he used this in a great paper. And it's still my belief that that's really a great data visualization. We did test it. We found similar results to the standard deviation. I thought it actually might be better. And in the end, because we were running this big high-powered experiment for cost reasons, we ended up not testing this one. We went with the hops one because it was even more extreme and different, and we wanted to see what was up there. But I can tell you that since doing this, even though we didn't see this work better than standard deviation bars, I personally prefer the bottom plot and have been trying to make more and more plots that look like that.
Yeah, super question, almost ESP. I'm kind of responsible because Jake was very much in love with the plot that was there, and I was like, guys, we're running like 3,000 subjects already. We have to like start cutting some of these plots that we want to test. But I think that would definitely be the next one that we do test.
And I'll also say that estimation. So Dan showed a plot of like a page of good plots, which you could quickly flip through that had those tweets and stuff. But on the left was actually a paper, like the Nature Correspondence, where these folks did a really great job. They have like an R package, a Python package, and a MATLAB package to make these estimation plots where they're kind of showing treatment with the points, control with the points, and then a 95% confidence interval around the difference. And so that's plug and play at this point. So that could be a really interesting one that's there for everyone to use if they want to check it out.
Yeah, I think the field is on top of this. Like, solutions are being actively generated. We kind of got in testing it right before that happened, but I think the next thing to do is to test these, and then there's the question of do authors want to adopt these, and can readers understand these?
A number of questions were asked about the sophistication of your sample, and a variant might be, what is the most sophisticated sample you've tried to use? I completely believe you would get your results again, no matter how sophisticated the sample, but it is more damning the more sophisticated the sample is. Yeah.
So as Jake said, I mean, we've definitely done this on like applied math PhDs, physics PhDs, stuff like that. Admittedly, they don't necessarily run experiments and they have such experience with it, but that's why we're very excited about these experiments that we're doing with Patrick, Michelle, and Chris with doctors. We're going to show these people graphs that would, supposedly be taken from medical journals and see what kind of inferences they draw about prescribing treatments to patients if they had seen this. Like, would you stop using the drug you use and adopt this new drug if this was what you saw? At the same time, we will also argue that there is a market. There's a huge market for consuming scientific results. The lay public consuming scientific results. When you read about things in the newspaper, you typically get just a mean difference, so no idea of variation, or maybe a mean difference in something about statistical significance. But we've done with Yasel Kim, we've looked through a lot of these media articles, and this information about variation in the outcomes is just pretty much absent. And so that's why users are a good representative of consumers of ordinary media, and it's also a good way to think about what's the easiest way to communicate this outcome variability. And we're very psyched that the height analogy seems to work really, really well and doesn't even require an extra picture.
Yeah, and Dan, I just want to add a couple of things to that. So one is, as we mentioned, we've kind of run this with people we know, and the experience is that the more you know, the longer you take to answer, but it doesn't seem to correlate so well with your accuracy. People have all kinds of interesting thoughts. It's kind of like, Bayes' reasoning problems, where you're almost certain you know how to do it, but then you make some terrible error. And the other thing is, we should get an interesting sense, if a bunch of people filled out the poll here, we should get an interesting sense of at least what people on the call thought, which we're looking forward to. The last thing I was going to say is that in the paper with Yasol, we did actually show people first, just mean differences or mean differences with standard errors. And what we found was that they often perceive, even when they don't have that information, they perceive the variation to be lower than it is. And sometimes showing the confidence interval or communicating it actually makes that worse than what they would have thought if they just saw the mean difference.
Should we call it a day, since it's 57 minutes after the hour?
That's good. You guys were great. Thanks so much for spending time with us, and thanks to the audience for sending in all those questions. Just as a reminder, all of those questions, even if they weren't answered, will be available to Dan and Jake after this, so they will be heard even if they weren't voiced. And in addition, we've recorded this video, and it will be posted as well. So if you want to come back and relive the memories, you can do that then as well. So thanks to Dan and Jake, and to all the panelists, and hope to see everybody again next week. All right, bye.
Thanks, everyone.
Thank you, everyone.